So now we're going to look at the different types of connections that exist in transformers. And the first connection, which is the simplest kind, is a three-phase delta connection. So here we have three different windings, which are the three different phases of this transformer, and they're connected in a delta formation. Okay? So two things that we need to get straight is the fact that there is something called the line voltage and the line current. When we talk about those things, is the line voltage is the voltage between each phase. So between B and C, B and A, and all the other different combinations. So then there's a line voltage, okay? That is from line to line. And there's a winding voltage. The winding voltage is the voltage of the single coil. So the winding voltage you can obtain if you put a voltmeter across the winding, okay? That is the winding voltage. The line voltage is if you apply the voltmeter across the lines. So make sure you have that straight before we start handling the math. Similarly, the other value that we look for is the current. We have a line current, okay, which is the current between the two lines. And then we have the winding current. The winding current is the current that goes just through one of the coils. So make sure that you understand what these values are and where they come from. Okay? The line voltage is the voltage across the two lines. There's three phases, so between B and C phase, or B and A phase, or B and C phase, that's the line voltage. And the same thing with the current, is the current between those lines. The winding voltage and winding current is only the voltage drop across each one of the phases. Okay, that's where I get my winding voltage or my winding current. And you'll see how this delta connection has very important properties. First, notice that if I put my voltmeter across the lines right here at these two spots, right, from B to C phase, the line-to-line voltage is 120 volts. And if I do the same thing with my voltmeter, but now I put it across the winding, just right here, you notice that I get the same voltage. So for a delta connection, the line voltage is the same as the winding voltage. So we say that the delta connection gives us a constant voltage value, and it's important for you to remember that. Okay? In a delta connection, voltage is constant. This is very important. So in a three-phase delta connection, the voltage is constant, meaning the voltage across the lines from B phase to C phase, B phase to A phase, whatever combination you choose, is the same as the voltage you're going to get if you apply the voltmeter across the single winding. You'll get the same kind. Okay? Now let's look at the current. The current, however, it's very different. Notice that if I put the current from the line to here, it's different if I get the current for the individual winding. If I want the current, notice that the current travels from here and from here. These two provide the total that goes onto the line. Same thing here. These two currents add to the total that go to the line. So the line current for a delta system is the vector addition of these two lines as they get of these two windings as they get there. Okay, the current that goes through this winding and the current that goes through this winding, they add vectorially to provide the current here. The current that goes here, the current that goes here, they add vectorially to add the line here. So what happens is that our line current is equal to the current in the winding times 1.73. Now you're wondering, wait a minute, where does this number come from? 1.73, yeah, going crazy. Well, it has a little bit to do with trigonometry, and just to give you an idea. Remember that each one of the phases that come through the AC current, they're 120 degrees out of phase. So knowing that they are 120 degrees out of phase, if you just take the tangent of 120 degrees, go ahead and do that in your calculator. Lo and behold, 1.73. So that's where the 1.73 comes from. It's because we have to add these vectorially. You don't go 1.5 plus 1.5 to give me my 3 amps. It doesn't do that. Instead, to get my line voltage, I do the current of the winding, which is 1.5, times the 1.73. We're going to look at some of these problems now using the delta connection. So here we go. What is the line current in a 3-phase delta connected transformer with a winding current of 1.5 amps? Well, they want the line current, okay, so this is what we're looking for. We don't know this. And they gave us the winding current. The winding current is 1.5 amps. So if we go back to the relationship, we know that the line current is equal to the current of the winding times 1.73. So let's do that. Oh, it didn't work this time. So the line current is equal to 1.5 times 1.73. So you get your handy dandy calculator. 1.5 times 1.73, and I get 2.59 amps. So as you can see, the current across the 2 phases, the current that I'm going to get here between B phase and C phase, right, is 1.73 times bigger than the line, the winding, the current in the winding. So the current in the line is going to be 1.73 times greater than the winding current. It's going to be very important for you to get straight that when we talk about lines is between phases, B and C phase, B and A phase, right? Those are my lines. The windings are the individual coils that are in the transformer. The other type of connection that we have for a 3-phase transformer is called the 3-phase Y connection. And this is the diagram of the Y connection. This also has some very important properties that you need to keep track of. So for example, let's look at the voltage and see what happens. Let's say that the voltage across the windings is 120 volts, right? It's 120 volts if I put my voltmeter here. It's 120 volts if I put my meter here. And it's 120 volts if I put my meter there. So the winding voltage is 120 volts, all right? But now let's look at the current. If I look at the current as it travels from B to C, the current has only one current path, okay? So that gives me 1.5. So the line-to-line current is 1.5 amps. And if I look at the current just on each individual winding, well, it was 1.5 over here, is 1.5 right there. Remember, these pretty much are in series, so it stays at 1.5. So basically, the line of 1.5 from B to C, from phase to phase, 1.5, is the same 1.5 you're going to get if you look at the winding. You get 1.5 here, and you get 1.5 there. So the current is what stays constant in a Y connection. And that's really important. The current is constant. I need to get a better pencil. So, in a 3-phase Y connection, what you need to keep track of is that the current of the line is the same as the current in the winding. That means the current is constant. Well, what happens to the voltage? Well, here's the interesting thing. If you look at the winding voltage, here's one winding and here's another winding. That means there's two windings per line connection. Do you see that? Between line B and C, there's two windings. Of course, because they are not, you don't add these linearly, you add them vectorially because they're 120 degrees out of phase. So the same thing that happened with the delta connection and the current happens here. The line voltage is 1.73 times bigger than the winding current. So the line voltage is equal to the voltage of the winding times 1.73. Okay? Because you have two of them as you go from line to line. But it's not 240 volts, right? You have to add them vectorially. We go back to the tangent of 120 degrees, and that's where you get the 1.73. So, again, what you need to keep in track for the Y connection is that the current in this Y connection is constant, but the voltage of the line is 1.73 times the voltage of the winding. So now let's look at a problem. It says, what is the winding voltage in C phase when the line voltage is 480 degrees? So they give us the line voltage is 480 volts. And I want to know the voltage in C phase. So that's my winding voltage. I don't know that. All right? So let's go back to the formula for the voltage. We know that the line voltage is equal to the winding voltage times 1.73. So I'm going to use this equation. Let me go back to my problem. I know that the line voltage is equal to the winding voltage times 1.73. So now I just need to substitute values, right? 480 is my line voltage. I don't know my winding voltage times 1.73. Man, I need to 1.73. So now you just solve for your winding voltage, simple algebra. You divide both sides by 1.73, and I get 480 divided by 1.73 gives me my winding voltage. So you get your handy dandy calculator, and you do 480 divided by 1.73, and that gives me 277 volts. So as you can see, we've seen these numbers before as electricians everywhere. This is a 277/480 transformer. So I hope that these two problems were helpful. We looked at a delta connection. To review, remember, in a delta connected three-phase transformer, right? Delta connected three-phase, A, B, and C phase, the voltage stays constant because the voltage across the line is the same as the voltage of the winding. Pretty much is the same. However, the current changes. All right? The current of the line is 1.73 times bigger than the current in each one of the windings. It's very important for you to keep track of that. And then we have the Y-connected three-phase system, right? Y-connected three-phase, A, B, and C phase, where the current is the same because it has one path. However, the voltage of the lines is 1.73 times bigger than the voltage across each one of the windings. Why is it 1.73 times? Because remember, these add vectorially. They don't add linearly. So you always take the tangent of the 120 degrees because these guys are 120 degrees out of phase. So that's where I get the 1.73 from, if you were wondering. Okay? The important fact to remember about the Y connection is that current stays constant in this connection. However, the voltage changes. So make sure you keep that in track when it comes to the delta connection, three-phase, and of course the Y-connected three-phase. Okay, those are very important properties that you need to remember about these two connections as we move forward.